All right, so dynamic translators. Brian talked about this a little bit in his introduction, and I think he asked me to drive this because I've waded a lot into a bunch of static translators, and also experienced the need for dynamic translators in trying to do this with dynamic languages like Node.js and stuff. But I actually know very little about how this is going to end up having to work under the hood, so this is definitely not going to be me explaining how to solve this problem. But similarly, it's going to be kind of a discussion. How many people here have used USDT that you know? Hopefully that's a lot of people here, okay. How many people here have built USDT providers already? That's a good number too. How many people did not do it based on the blog post that I wrote at some point? You gave me all the information for the blog post. Cool.
Not cool.
What?
I mean, it's like scary.
Well, not that part of it, but like a lot of people here have experience with this. So USDT is obviously great, right? It gives us a lot of nice things, but we're talking about the limitations here. So I want to get that out of the way. This is a hugely powerful thing that allows us to trace all kinds of stuff about userland applications. And I think the example with Mark Cavage's Restify is great. For those who don't know, this is a library for Node.js for building web servers, and it uses this interface which is used in a lot of dynamic languages now, where you register some number of handlers to deal with different stages of the request. So you might have a handler that parses the headers, parses like the authorization, deals with content type, etc. So you kind of have this pipeline. And if you're using this library, you get dtrace probes for free at the start and end of each of these things, which lets you quickly identify where latency is coming from. Like, for my request, how long is each of these stages taking? It's an incredibly powerful thing to have, and you basically just get it for free with this library because of USDT. The downside of it, though, is that we're using these dynamic providers, so we can't use static translators because these providers don't exist until this program starts running. And you get like 6 arguments, and there's 6 primitive arguments for your dtrace probe. So there's kind of a limited amount of information that you can actually pass. So this is one important use case where you actually really want dynamic translators. You want, when you cons up this provider and you have a bunch of probes, you want to be able to say, and here's what the structure of these arguments looks like, and I want them to appear like this to a D script. That's kind of one use case that I have in mind. Another use case is to address the versioning problem that Brian alluded to, which was in the Node provider. So Node.js itself has a provider for various operations for HTTP requests, start and done, and has a couple of structs with a couple of fields. And at one point, I wanted to go add a field to one of these structs, and this turned out to be enormously more complicated than you would expect that it would be. And part of the complication here is that you get one node.d provider file, one node.d file that describes the static translators for this thing that lives in userlib dtrace, and it has to know about all previous versions of the node binary. And even that seems like it wouldn't be that bad. It turns out that's also pretty complicated to get right, and I didn't get it right. And that was unfortunate. And in very subtle ways that you would only notice if you ran dtrace in certain ways. But anyway, the idea with dynamic translators is to encapsulate all this information with the thing that you're actually instrumenting, which is where you actually know what these things should look like. There's another problem here that is also worth mentioning that we get hit by a lot, which is for almost any translator that uses any static translator, you need to know whether you're looking at a 32-bit or a 64-bit process. The way you do that is by looking at CurPSinfo PRD model, which you can't do inside a local zone. So you can't actually use most of these static translators inside a zone unless you build a custom translator for the 32-bit or 64-bit application, and then you can use -L to use that file instead of the one you use with dtrace. So there's kind of a lot of these rough edges that we want to address with this thing. I don't know how we do it. So, yeah, I don't know, where do we start?
Well, I'd like to just differentiate. There are 2 different types of dynamic translation that are worth talking about here, and Brian kind of touched on both of them in his introductory comments. One is kind of global variables, like if we're talking about the FDs array. So that's like a kernel component, and if we're talking about like the IO provider, or if we're talking about the SCED provider, those are kernel level statically defined tracing providers or global variables. I think that's kind of one mechanism that we need to discuss. and today it uses a very different mechanism than usually in static wave font tracing. I think the other one, as Dave was focusing on, is around USDT providers, and that's probably where the pain is most acute, and where we bump into these horrible burrs like the dummy structs and all that kind of stuff.
So is there a need for dynamic translation for kernel stuff, or is it sufficient to just say like, well, keep your user the dtrace in sync with your kernel?
Is there a need?
Is it sufficient? Like, if you just said keep your user the dtrace in sync with your kernel, and people did that, would there be no problem, or is there an additional problem?
So there are a couple of additional problems. One is the problem of kind of privileges. If you want less privileged users to be able to like chase pointers in constrained ways, that's one problem that you might be able to address with the dynamic translator for the kernel.
That's the Curpius info PRD model thing, for example, that I was talking about.
And Dave used that example in the context of wanting to write a userland translator, but there's actually a kernel-land translator tied up in that as well. So that kind of mixes both of those. The other is, again, where we kind of reached the end of the road with dtrace and then figured out how to make do anyway. One example is with the dummy structs, and the other example is with, for example, the NFS provider. So the NFS provider, I won't go into a tremendous amount of detail, but it does some horrible tricks. The notion of a translator is to go from one type to a translated type, which is great. I've got a buff, I want to go to a buff info T. You can go, everyone with their laptops open can go into user lib dtrace io.b, and you can see how that thing is translated. Some of them are prettier than others. If you're on your Mac, in particular, apologies Steve, you'll see some kind of an amusing thing. So for example, if you look at your file info T, maybe you've wondered why on your Mac, at least in the version, I'm a version old in Mac OS, so maybe this has been fixed in mine. You wonder why do I only get two elements of my path on the Mac? I get the file name and the file name and its containing directory, and then I don't know. So if you look at the translator on your Mac, you'll see immediately why, because that's kind of the information that's available, or maybe this would be solved with iteration, for example, I don't know. Anyway, what the hell was I talking about?
Is there reason to believe that these two problems can't be solved with the same underlying mechanism? It seems to me that it's not much of a stretch for the single mechanism to solve both problems.
No, so I think it's not a stretch to think about solving both of them together. I think what I'd like to do is focus our discussion first around userland and then talk about how we can apply that to the kernel. Because I think there are some ways that we can do that in ways that we've talked about and ways that I've thought a little bit about.
So I guess it might make sense, I sort of skipped this, but it might make sense to talk about how the static translators and providers work with that today. Does that make sense? I mean, I'm happy to do that, but.
Sure. I just ask, is anyone interested in 2 minutes on the genesis of USDT? Okay, great.
Yes.
Nobody. Oh,
I am.
There are a couple of people. Okay, so forgive me. But in the waning days of dtrace, as we approached the initial integration, we had been talking for as long as I had been in Sun, I joined Sun in 2001. We've been talking about a utility called Plockstat, Plockstat. Lockstat was introduced by Jeff Bonwick in 2.6 for looking at kernel level locking primitives. One of the things Brian did fairly early on in dtrace to kind of prove its mettle was convert Lockstat to Lockstat became a dtrace provider, and the Lockstat command became a very simple consumer of dtrace. Medium simple consumer of dtrace. But we really, well before, I don't know, when would you say Rogers first started talking about Plockstat?
Yeah, in probably 1999. I mean, we knew we needed to do, Lockstat was very successful, and we knew we needed it for a little while.
Right, and this is, I mean, Lockstat is tremendous. People have used Lockstat, people have used Plockstat, like that. So understanding lock contention or hold times or anything in your user level program. Now, there was some kind of abortive attempts, I think, at Plockstat that used like breakpoints. It's like, hey, guess what? If you're breakpointing your program, you're probably chasing away every kind of locking pathology you could ever conceive of. So that fixes your problem, right? Just use that version of Lockstat. So the first version of Lockstat that I kind of proposed was I didn't know at the time it was garbage. I mean, it was just garbage. And I'd hacked up every user level locking primitive. And Brian, I think, very helpfully suggested there might be a better way of doing this, and we ripped it out, and it didn't go in with the original dtrace integration. And we thought maybe there's a more generic implementation, a different way of instrumenting statically. If you look at talks Brian has given at various times, you can hear him say that USDT was created in support of dynamic languages. False. Like it turned out that it worked out great.
That's a straw man. Have I said that? Do I claim that?
You can debate yourself from the past. Everyone would love to watch that.
I'll debate myself.
But it was really created in support of p-lockstat. USDT has this very complicated mechanism where it makes extensive use of like ELF information and relocations. And as people have noted, it's a little bit complicated to actually wire it all up together, and that's why everyone uses Dave's blog post. But it was originally intended for use with libc and to create these probes that are associated with lockstat.
Do you want to talk about the lazy loading? Because actually I think that's a very interesting property that only Blockstat or libc really uses.
It turns out there are other providers that use it too. I'm happy to talk about that. So one of the things that, again, was super duper important in 2003 was making sure that when you executed programs, they started up very, very quickly. I think there was some benchmark that Sun really cared about, which would basically execute a fork bomb and count how long measure how long it took. I don't know that is still a representative workload, but we were very concerned about. We didn't want to slow that down basically because we'd get the fork bomb police to show up at our house and tell us that we've slowed down their fork bomb. And it's not all, basically you spend half your time making sure no one was trying to shout at you for slowing down some benchmark you needed.
Because Linux goes faster.
Oh yeah, also Linux executed the fork bomb way faster. There you go. So what we invented so most USDT, the way USDT works is you compile it into your program, and that includes an init section. When you start your program, the init section executes and will send it encodes all of the information about your DOF program at compile time, or about your USDT provider into a DOF ELF section. Then when you start your program, it will ioctl all of that information into the kernel and hang it off the proc structure so that that information is living downstairs. That takes time, right? You're moving potentially a bunch of data. DOF is not the most space efficient encoding of these bits that you see here because it didn't need to be. So it takes time to just move the data around. So when we started, we didn't want to make it so that every program that linked with libc, aka every program, was going to incur this fairly expensive, relatively speaking, tax. So we created this notion of lazy loading. So if you do, I shouldn't even tell you this because I don't want you to do it. So people here and at the internet don't run this, but if you do -x lazy load, it will not generate this init section. So when you load your program, your USDT provider will not be there. And it will later be loaded when you use dtrace or p-lockstat or some of these other programs to go look for that USDT section. Now, anecdotally, we had an interesting thing happen at Delphix where I work. We do a lot of work with Java, and we noticed that in addition to these USDT providers, we also have our JStack helpers are all in this same DOF bundle. So if you say -x lazy load, it doesn't send it down when you start the program. What we saw at Delphix was when we tried to record Java stack traces, we weren't getting the fancy JStack output. It wasn't doing the obscure translation from addresses into Java symbols, for example. And what we found was that the hotspot folks had done things lazily, presumably because they had some benchmark which measured the execution speed of startup time of Java, and we had regressed it by 0.5%. Or just as likely, that benchmark never was run, and people were just worried about regressing it, which is totally legit in that climate. Anyway, so what we had to do is we had to force that DOF to be loaded down into the kernel in order to get the access to the JStack, the JStack translators. Did I cover whatever it was you asked?
Yeah.
Okay, good.
How did you actually muck the binary to
No, all we did is we did something like this. We had a little program that did dtrace -n, xxx, and then like 1, 2, 3. And then we after we started Java, we would run this program, and it would say, "Hey, no probes matched." And we're like, "Oh, thanks for looking." And what again, as I discussed earlier, when libdtrace sees something that ends in a number, it says, "Hey, maybe this is a PID." So I'm going to go look for PID 1, 2, 3 and see if it has a USDT provider called XXX. And the way it does that is it finds all of the DOF that contain it helpers, sends it downstairs, asks the kernel, and kernel says no.
So we should never lazy load. This is actually a good warning that anything that has a UStack helper should emphatically not be lazy loaded, and we just never conceive that something would do that.
Exactly.
So the problem, I mean, sorry if other folks aren't, it's kind of dawning on me, but I understand the problem now, that you're not even instrumenting, you're not using the PID provider at all. What you're using is you're instrumenting the kernel or what have you, and you're using the JStack action. So we have never told this thing to IOCL down its helper DOF, because we don't know that you're not instrumenting it. You're instrumenting the system, and then you're using the UStack helper.
That's right.
And the problem is that we honor their idea to be lazy loaded with the UStack helper. That should have been IOCL down.
And there's another mistake here too, which for that dtrace made, which is that all of your USDT providers, and I'm sure, Dave, you've been on the coalface for this, have to come in at the same time. You can't have multiple DOF sections. You have to define them all at once. And this is also reflective. I know a bunch of people on the list have had problems with .a's. There's a bunch of very rough edges, and some implicit.
That rough edge seems awfully sharp, and it just took my arm off.
Yes, it's more serrated.
That's right.
So. I bet what the Java folks had been relying on is being able to create their DOF for their JStack helper and their DOF for their USDT probes and send them down together. One, it makes sense to be lazy. The other, it doesn't. And when you squish them together, you have to choose for all of them, and they made the wrong choice there, or they made the choice that makes it harder to use JStack at least. All right, where were the dynamic translators? Oh yeah,
well,
that was my 2-minute aside about
well, you kind of described how USDT providers work, at least in the context that matters for this. So the idea with static translators, if it wasn't clear to people who you just don't already know, is when you run your dtrace enabling to actually use a USDT provider with translated arguments, when dtrace loads up, it reads all the files in user lib dtrace to read all of the translators that are defined there. And then when you fire a probe and this is the part I'm a little bit hazy on, a probe that is defined to have arguments that it knows there should be a translator for. Then it goes and looks in the library of translators that it read on startup and executes the translator, which is a bunch of D. It's basically written declaratively and describes, it's basically like you say, okay, I'm translating from, in the simple case of,
you notice cat one on your screen there, just cat name.
Yeah, that's a good idea. I can't type. What's a good one here? Maybe, there's no.d, but...
IO.d or part of
yeah, IO.d.
Or proc.d is
Yeah, this is the file info.
So the file info one is here. Can everyone see that well enough?
Yeah.
So this is one that's actually in the kernel, so it's a little bit simpler. But what we're basically saying is the probe argument is a file info t, but the argument that the kernel actually passes when it fires the probe is a struct vnode. And this is how you translate it. And it's member by member. So to create the FI name field of the file info, you evaluate this expression here. For userland, these look...
yeah, so you have no.d there, I think.
Yeah.
Or
And this is going to basically get compiled into the D program that, userland is going to take this, compile it with the D that you write, and then the diff will do these dereferences and question mark colon operators and whatnot.
It's much more like a macro than anything else. We're basically taking that code, slopping it in, and then compiling it.
What you're describing so you said the compiler, you meant the compiler at the time. I
think I see these.
Right now, it's
like I said, it's like a macro where you process
yeah.
whenever you say FI path, inserts that.
That's right. Node.d, yes, that's
Sure.
right.
Node.d is particularly gnarly.
Do you have the suicide note in there? There it is.
Yeah. So here we're creating a node HTTP request T, which describes a node HTTP request. And the thing that so the way this one works is the way a lot of USDT providers work, probably because they all come from the same original source, which is that the application always passes the same basic struct, and the translator just picks the pieces that it needs to fill in the pieces that it needs to provide to the probe. So what we're looking at here is the description just for the URL field here. This is all for the URL field. So what we're doing here is we're switching on the version number in the struct because of the versioning thing that I described, where I had to extend this struct, so I had to add another field. But we didn't know in the translator if it was going to be there, so we had to add a version type field as a sentinel for that. And then you have to switch on the process model, and then you have to do all these gnarly copy-ins to actually get to the thing that you care about. So that's what these things look like for. Well, this is a particularly complicated user interface.
Can you pull that back up, Dave? Because
Yeah.
I think that demonstrates another serrated edge of USDT, or of translators, because translators know how to translate from one type, in this case, the node dtrace HTTP server request T, to another type, which is the node HTTP request T. Now, this gets to why you have these kind of these dummy types. Basically, we use this as a trick. In this case, node dtrace HTTP server request T. That was, when we created translators, that was intended to be the native type. Now, believe it or not, Node does not have a native type called that. We use that more or less as a sentinel to say, hey, this is basically a UUID that says execute this translator. If you looked at the io.d translated types, you can see that where this idea came from. We're saying, hey, if you have a vnode, then translate it into a file info T using this way. Or if you have a file T, translate it in this way. It kind of makes sense. Now, when you're talking about translators which are highly specific to USDT probes, translators that you don't want to ever be reused in some other context, because it would almost certainly be an accident, that's where you start to get to this really goofy stuff.
So basically, like, you created this node dtrace HTTP server request T just to be the argument to the probe.
Yeah, it's actually even worse than that, because that argument, it is, as Adam said, it's kind of a UUID that's synthetic and it's defined. It also exists in the actual node add-on, and those definitions really should match, hopefully. But there's no enforcement mechanism.
Well,
so
the definition in the provider file, in the translator file, there is one up here, I think.
right, there's got to be, yeah.
That one should match whatever the application passed in. But there's another reference to this in the actual provider file, which is the thing that gets compiled into the application, which it doesn't have to match. Because that doesn't get compiled into the application. That's what we want to do.
Right.
But we came to talk about the future.
Yes, exactly.
So this is, I think, the takeaway here is that the current state of the world is frankly horrible, and right.
That's the current state of the world.
That's the current state of the world, and it's not even just the kind of copyings which make it horrible. I mean, it's all horrible. But I think what this highlights is there's actually probably some language changes that need to happen in D when you're generating a USDT probe, when you're creating that definition. Because when you create, what you want to do is be able to translate some arbitrary set of input that you get from that, at the probe firing time into some, types that make sense for the user. You don't want to have to leave behind a UUID as a cookie crumb to the dtrace language to say, now execute this translator. You'd rather have that just be kind of tied up and implicit in the definition of the translator and the definition of the probe. So my guess is there are probably some language changes that need to happen to really accommodate this in a way which is palatable. Then the next step is to, you've changed the language, you need to change the compiler. And in particular, you need to change the compiler to take those translators, translate them into DOF, and leave them in that USDT DOF, which will eventually be ioctled into the kernel.
But some of that does exist, right? That is some of the compiler changes that have been made.
Right. So I guess this is what sort of exists with the with the xlate equals dynamic. I think we need to reassess the kind of end-to-end life cycle. Even when that was done, we really didn't understand USDT.
Yeah, that's
USDT is definitely an emerging intelligence.
You have a DOF section though that describes the translator. I mean, I think you do have. I don't think any of it's wrong necessarily. I just think it's not.
I think it's both not enough, and I think it again it's not reflective of where USDT has evolved to. I think there's still input and output types. I don't think that's going to fly. So then, we've encoded that in. We then, in your dtrace program, we need to know that we're going to generate, as Brian's, as the mail that Pacheco sent to Brian in 2005 clearly stated. If you look at home WS source dtrace, may it rest in peace, is that we need to then generate instructions, the special instructions in the dtrace programs that you write that will then invoke those translators which are embedded into your DOF. Now, if this sounds a little bit like subroutines that you're defining in dtrace, it is. So that means we have to generate, we also need to do extensive levels of checking. Let's say you have generated some DOF in your USDT bundle that itself tries to execute xlate instructions and creates kind of like recursive loops of xlates. That's a huge pain in the neck. So maybe we make it so that xlates can't, translators can't use the xlate instruction. Maybe that's not so bad. Maybe it kind of is. So
and so like, this is just an instruction that says do this translation, and the kernel kind of its code rather than.
Well, let me transition to talking about the kernel. So I think you're on something there. So we've just been focused on the userland probes and translators which pertain to those userland probes. So when you talk about privileges, I think the way we say that is if you can execute that probe, if you have privileges to enable that probe, rather, when it executes, then its translator follows the same privileges that you have, namely accessing the traced process, for example. So it's unlikely that you have a USDT helper provider whose translator then needs to look at something in the kernel. I think that would be outside the scope of just the userland conversation. Then it's worth talking about, can you pull up SDT subber?
Yeah.
For everyone's enjoyment.
Enjoyment is.
Enjoyment says hard. So the way that kernel level SDT works is very, very different than the way userland SDT works. And because I have the stage, I'll say that USDT is approximately 1 trillion times better. So here's how kernel SDT works. So let's take, for example, the I/O provider. Let's see.
Seems like the most elegant way to do it to me.
Exactly. So here's the I/O provider. Now, oh, wow. So this is I/O start. So what this says is, excuse me, is that we should take for the 0th argument. I always get these backwards too, so you'll forgive me. So
I think I got your original source to block stack.
I have the microphone. So this says for the 0th argument of the start provider, of the start probe, whose type in the kernel is a buff T star. Pardon me. For the 0th argument, I want you to take the 0th actual argument to this probe, which is a buff T star, and I've translated it into a buff T info. So the arguments here are provider, name of the probe, the argument to which we're translating, the argument from which we're translating, then the type of the argument from which we're translating, and then the type of the argument to which we're translating. It's kind of an ABBBA. I can't remember what that is in kind of poetry, but that's keep that in mind, because this is poetry.
First of all, I think it is.
So this is how kernel this is how the kernel types work for SDT in the kernel, and all of this is used as kind of seeds for the translators. Again, libdtrace will IOXL down to the kernel, say what are the input types, what are the output types, then it'll figure out what translator to then use statically.
The kernel does very little with this other than take it apart and hand it back to userland
Exactly. So this is just a static table. Now, it is, I'd say it's one use case that this makes difficult or impossible is creating a SDT probe with translated, SDT provider with translated types that lives in a kernel module which doesn't exist in Illumos. Probably not a use case that we care about, only one that we sort of cared about in the glory days of Sun. But it's worth noting nonetheless. So I think in order to get to dynamic translators for the kernel, I think the easiest path is to do a KSDT, analogous to USDT. So have the same mechanism where there's DOF that's loaded into the kernel modules, some part of the kernel linker or the kernel kind of linkage process would kind of pull out that DOF and feed it over to dtrace or leave it in a location for dtrace to pick up.
So I totally agree with you, although I don't think that, I think you could do the kernel translation bit without actually doing, I mean, you could decouple those. Those things could happen asynchronously. You don't need to do KSDT, because you're still going to generate the translator will be dynamic, you'll generate the DOF, it'll go onto the kernel. It's just that it will have a, you would not need to do KSDT before you did. Not that I naturally resist it or anything.
I think that's technically true, but I think that you would be building potentially a bunch of false work there, which is a word I learned.
Yeah, I mean, the only reason I say that is because the translation issue is much more burning than the asynchronous module issue. It's an issue, but
yeah, I agree.
But the translation issue is.
I'm not necessarily convinced that it's less work to do it that way, because I think that again the mechanism you want in userland would say. Not just how do I translate one type to another type, and maybe just the current array of kernel probes. This is sufficient for. But I can tell you anecdotally that's not the case. For example, if we look at if we look at nfs.d, then here we're getting to some real nastiness. So here we've got a kind of crazy translator here. And the way translators are supposed to work is it's supposed to say, take the input type, which is called P, and translate it to the output type. Now what this does is in NFS, as I alluded to, we have stuff in we have stuff in multiple structures which we want to translate into a single structure. So what this elegantly does is it takes arg0, which we know is going to be of type struct service request, star, and it takes arg1, which it knows based on the context where it's firing. So, for the existing kernel SDT probes, we've already hit the end of the road of what translators kind of will do. Now, again, maybe it's like those aren't the use cases that we want to enable with this.
But you're going to do it at the same time. I mean, you're right that it's like once you've done the kernel translation part, it shouldn't just fall out.
Yeah, and the other thing that, one thing that Eric had requested was, I think it was from you, from the kernel is enabled probes. So another thing that would fall out of doing KSDT is kernel is enabled probe. I mean, it would take some work in FDT or SDT or wherever it's going to happen. But it would take some work to do that. I think the last piece of it is the global variables. So today we define the FDs. Let me pull that up. So has everyone used the FDs array? No? Great. So there's this array called FDs. You can put in a number, and out will come a file info T, and here we can see the translator below. And it happened in version 1.1, so way back in the day. Again, with these global variables, again, we might want to have some dynamic translation. Maybe it's sufficient to have static translation still for global variables.
That we need. This is
right.
This is
right.
what's killing us.
And this is where now you want kind of privileges associated with these global variables or something. So maybe you want it to be the case that any translator that you have in the context of KSDT or in some DOF that lives in the kernel has associated with it privileges, which is not something we do today. It's something today privileges are really expressed on the level of the provider. I think this might require some alternative privilege mechanism where you can say, hey, here's a variable which I'm defining in DOF, and I want users with the following privileges to be able to have access to to this translator. That's a mechanism which doesn't really exist. And we like translators would need to have implicit with them or explicit with them the privileges associated with them to know whether or not you can execute it. But as Brian says, this would let folks who have less than dtrace kernel or people who are living outside of global zones in local zones to execute these chunks of important DOF code that correspond to these important parts of the system. Other comments on dynamic translators, on kernel STT, on any of this stuff?
What's the first step?
So I'd go usually in first. Like,
Sure.
I'd say the first thing is to spend some time with a couple of people and a whiteboard and figure out what language changes would be required. So
I think the first thing would be to decipher what's already there and figure out how that works and whether that's going to be. I think it would help inform that conversation.
Well, I'd say to pull into reading material for that, it would be not just what's in libdtrace in the compiler and not just what's executing in the kernel, but also the providers that a sampling of providers to make sure that we're addressing those use cases. I'd take some of the complicated ones. The NFS provider in the kernel. This doesn't have it up, but the node monstrosity that caused Dave to write this monologue. A couple of these hairy providers to make sure that we're addressing those use cases. And then look at language changes or if there need to be language changes indeed, in the context of rewriting those providers to be rational and sane. So what would that node file have looked like? I don't have it up, but what would the NFS file look like?
Write the provider.
Yeah, right. Let's see what we want it to look like, and then kind of take a sniff at it, and then post it to dtrace discuss and see if it looks like it covers a bunch of use cases. Get different people to kind of rewrite their providers in this context, because I think we'll learn a lot just by experimenting with the language and figure out what that needs to look like.
So can I just ask, how many people is this important enough to be able to dedicate some significant resources to this? Just by show of hands. The significant resources, I mean, this is something you can do, if not part of your day job, then significantly. Because just want to try to figure out if it's just us or not.
Adam, do you guys, to what degree is this, I know there's a problem that you...
This might be really useful for the ZFS provider.
Okay.
I mean, one of the problems here, Brian, is like it only kind of matters most acutely to the people writing the providers, but what I think the people in the room maybe don't realize is it benefits the users of those providers as well, right?
Oh, I'm just trying to actually get kind of a list of names on the whiteboard. Because we have to solve this problem, so I want to be sure that we got the right people in front of the whiteboard if that's the first step.
So we may have a use for the kernel side of this, right? But I don't think I don't need to use on that side.
So the other use case here, which I think is pretty important because I think it goes to enabling people to write providers who otherwise wouldn't have. Like the dream here, or at least one of the dreams here, I think is taking Mark Cavage's Restify thing. That thing should be able to, in JavaScript, basically say, here are my probes, here are the arguments I want to pass to this thing, and have some way of translating that to native, obviously. And like, that's it. And then it just ships that down, and then someone who's just writing a JavaScript application or a Ruby application or a Python application can define a provider with structured arguments and then use dtrace to actually understand that thing.
Yeah, I was just going to say exactly that. I mean, what would be nice instead of having this stuff listed using dtrace? You guys already said this, but effectively like bring that into the app so that when you, I can show an example later, but effectively what it looks like when you create a dtrace probe in like JavaScript or Ruby or Perl where Chris has done that work is you just literally in the dynamic language say, hey, make me a probe and here's my arguments, and you get the magic number 6 due to the number of registers, and they have to be char stars and ints. And what would instead be really much nicer is if I could just say, make me a probe, and oh, by the way, here's a translator for this much richer thing I want to pass down, and I mean, the lecturing would surely be like, I can do that in JavaScript or in Python or in Ruby, but I mean, if you still have to like do this in D, I think that's fine too.
The goal of all, at the end of this, we know that we succeed to some degree because usually dtrace would be gone. Right? There'd be nothing that needs, except for the ever important drti.c, or drti.o, which I'll talk about as much as people want me to.
Or as little.
We have 5 hours.
No, oh, listen, we got 5 hours left. Great. Cool. Other people want to speak up for being interested in talking about how to generate these things. Yeah. Got that makes sense.
Picking apart the Erlang data types, which have very little to do with the C data types, would make the node translators look very simple in comparison.
In other words, the problem is much more terrifying.
Yes.
Yeah. I mean, to be fair, in the node case, it actually is basically a C struct with a bunch of fields. It's actually not that complicated,
Right.
conceptually.
That goes back to dynamic CTF generation, though, right? What we'd really like to do, I would think, is for the non-translated types, you generate not only the definitions, but also the actual structures, the CTF itself, the non-optional data.
Yes.
Is that crazy?
I think I just burst a blood vessel thinking about it, but it's not crazy. I think it's just complicated. It's just crazy complicated.
Sure.
Yeah, especially in terms of what lives downstairs and what lives upstairs, because I think the easiest way forward is basically the lib dtrace kind of learns about all those types, and I don't know how we kind of connect the dots from the. I mean, one thing that's kind of tied up in here that we haven't really talked about is that we should have, is that part of this is that when we create the DOF for those translated types, that DOF needs to contain effectively C structure definitions. It needs to either have embedded CTF or something, so that when you get those translators, you know what the type definition is of them. We definitely did not exercise that. Either there needs to be embedded CTF within the DOF, or when we take the DOF downstairs, we need the libdtrace needs to pick it apart and then create a CTF container which contains those types.
I think it already does. What is specified is in the translator table in DOF, dynamic translator table, that specifies the input and output type, and then that gets compiled just in the diff, right? And there's no additional type information, to the best of my knowledge, that comes out of that, right? I mean, again,
Yeah, maybe we could pick that apart and put it.
Yeah.
I think there's also an issue or an interesting issue with all of this in terms of like 6432, like the bitness of the system. When a probe fires executing the right translators, maybe that falls out. I haven't thought it through.
Yeah, I mean, you definitely have the case where if you could have two applications. We talked about this solving the versioning problem, but it kind of punts it because you could have two versions of Node or whatever it is that have different translators for this thing. When you're instrumenting it, when you're compiling the script that actually uses this thing, what do you do?
Yeah.
Do you know what I mean? We have to figure out how to resolve that.
I think you assume that the translator itself is translating into a stable type that is neutral across versions and so on.
Yeah.
So
Well, but that's not the case in the case where you want to add things to new versions of the thing, right? In the Node case, you want to add a new field to this thing.
Right. Judging by the room, I think we've kind of exhausted this topic a little bit. Obviously, it's nasty. I think it's an important problem for dtrace moving forward, especially to enable a lot of these use cases. Better userland, statically defined translated, SDT, user, let me try again. Better userland probes, and then also these use cases where you have unprivileged users looking at kernel level objects. So